Now let's talk about the three-dimensional load application, all right, as we show over here. This is different from what we have reviewed before. Okay, for all the other cases, the forces are applied along the same plane. Now you see forces are along different planes. Okay, Fy is in the xy plane, and Fz is in the xz plane. All right. So this is the shaft which has a length of L and it's fixed at this end. Okay, we use that blue block to represent a wall. All right, this is the cantilever beam. All right, so we can solve the bending moment very simply. All right, of course, we can combine these two forces into one, but in order to show the details, because in real application, the load could be at any location, all right, not just at this one location. But at this end, we know all the forces already. We don't have to solve the forces at the other end, so we can just simply plot the bending moment diagram as I show you over here. All right, so for the moment produced by Fy, okay, moment produced by Fy, if we use our way of identify the moment, okay, the thumb pointing to the z direction, so that's why we call this moment moment mz. All right, so Fy by x give us the diagram of this bending moment. It reaches the maximum at no one end, which is Fy by L. Likewise, we can do the same thing for the moment produced by Fz again. So the moment actually use our thumb, that is along the y direction. That's why I call this moment my. All right, we do the same way. We figure out the largest is at no one end, which is Fx by Fz. Fz by distance L. Okay, so the resultant bending moment is at the, again, the wall side. Okay, that has to be the vector summation of these two things. Okay, so it shows by this equation. Maximum bending moment at the wall end, that is a square of this plus square of that one, and take the square root. All right, so which point give us the maximum bending stress? That's of the most important meaning, because we want to figure out the point of the most critical situation. All right, so let's move out this circle at the wall to here and enlarge that a little bit. You see here, that's the situation. So this is you see the same coordinate system z and y, but this is at the wall end. All right, obviously the bottom point, okay, along the y-axis, and that give us the maximum bending due to Fy, okay, which is the white dot I'm showing over here. Similarly, for this effect by Fz, which is along the z direction, all right, this white dot over here shows the location of the maximum bending in tension. So those two white spots are for bending in tension due to those two forces individually. So combine the effect which give us the location of which is the most critical point, okay, that give us the maximum bending, has to be between these two white spots. Actually, it is along here, okay? The red dot shows the location of the maximum bending stress in tension. Of course, the other side is in compression. All right, so now we have a three-dimensional load application. How about the stress state? Do we have a three-dimensional stress situation? No, we have a very simple 2D stress state. Okay, you see here along the red dot, we only have tensile bending stress. That's it, okay, which is here, as I'm showing over here. All right, just move this red dot out. All right, that's the bending stress, okay, simply as what we learned before, nothing new. All right, basically, so we have very complicated load application, not very complicated, but complicated three-dimensional load application. All right, we end up at our most critical point. We still have this just plain stress state of only the normal bending stress. For this case, is tension. Of course, the other side, as I mentioned, is in compression. All right, that's the end for this review.